Hello everyone, this lesson is on atomic structure. So, we will be discussing Bohr's model of the hydrogen atom. So this is the second part, which is we are to quantize the electron orbits. So we will be using a classical approach. So recall in the first part, we have determined that the angular momentum of an electron orbiting inside the nucleus of a hydrogen atom is given in this equation. L equals an integer n times h bar. So we say that the angular momentum of a particle is quantized by h bar amount. Okay, now what Bohr did is to develop a Newtonian model of the hydrogen atom. So say you have here a proton and an electron. So the electron will orbit in a uniform circular motion around this proton. So this is a H atom. We have one proton and one electron. So we know that from classical mechanics, uniform circular motion must have a centripetal force. So we know that Fc should be present for this electron to move in circles. So that centripetal force will arise from the Coulombic attraction or the electrical attraction between the proton and the electron here. So that Coulombic force, the magnitude of the Coulombic force is given by, let's call the Coulombic force F sub E. So it's given by K, which is 1 over 4 pi epsilon naught times Q1, Q2. But since we have a proton and an electron, they both have the same magnitude of charge, we can say that it is E squared over their separation distance r square. So this is our source of centripetal acceleration. Okay, I forgot to put in the radius of orbit. Okay, now so we also know that this electron has a tangential velocity component. Let's call that v. Okay, so we know that all forms of uniform circular motion has an acceleration of AC equals v squared over r. Or if we want to get centripetal force, we multiply by the mass, we get MAC equals mv squared over r. Okay, so we will equate the Coulombic force to this centripetal force. So we would have Fe equals Fc. So Fe is 1 over 4 pi epsilon naught E squared over r square equals mv squared over r. Okay, so what we are going to do here is we want to determine the radius, because if we do so, we will now know the orbit of the electron. Or moreover, we will also see that the orbits of the electron is actually quantized. So let's determine R. Okay, so we will do so by utilizing our previous result, L equals NH bar or L equals MVR. So we will find a term wherein it involves mass times velocity times R so that we can put in this result of L equals NH bar. So let's see, we have R square here, we have R square here, we have M, we have V squared. So let me move MV squared to the left hand side. So we will get 1 over 4 pi epsilon naught E square over R square R square M V square equals 1 over R. Okay, now I want this term to be R square, M square, and V square. So what I'm going to do is multiply this by 1, M over M. So now I have E squared times M all over 4 pi epsilon naught R square M square V square equals 1 over R. So now this term is L square and L is NH bar, so we would get N squared H bar square. So this term becomes N square H bar square. Equals 1 over R. Okay, so now inverting 1 over R, we get R equals, we have N square H bar square 4 pi epsilon naught over E squared M. So this is R, meaning it must have units of distance. This is an integer, so it is unitless. Now with the argument, with using a logical argument, this term should be in units of distance. So this is actually called the Bohr radius. So they set a specific value for it. So A naught, or the Bohr radius, is equal to, if we simplify all these constants, so H bar squared is a constant, 4 is a constant, pi is a constant, E naught is a constant, E squared is a constant, the mass of the electron is a constant, we would get 5.29 times 10 to the minus 11 meters. Okay, so we will see later on that this equation, this value the Bohr radius, can also be solved using a quantum mechanical approach in the Schrödinger equation. So take note, these are two very different pictures of the electron, but somehow they arrived at the same constant. So some physicists say that this is actually the most serendipitous result in all of physics, because one has a derivation using a classical approach and the other has a quantum mechanical approach. So what are the odds that the two would have the same constant? So in other words, Bohr was a very lucky person to arrive at this constant. Okay, so actually our goal is to solve how the electron orbit is quantized. So we see that R equals n squared times a naught. So this is our final result. The electron orbit R is quantized by this Bohr radius. So we would have values of n ranging from 1, 2, 3, and so on. So for example, if n equals 1, the electron orbit would have its minimum distance from the proton. So the electron would be orbiting 5.29 times 10 to the minus 11 meters away from the proton.